Okay, I'm just going to minimize it. Let's start the designing part. So till here, any doubt, people? Okay, so I hope you got the point, right? Okay. As I told you, we're going to use this Excel sheet, right, for everything, right? What is the first thing on this Excel sheet? So these are all the just name of the pins and name of the signals. We're not going to use this here. And obviously, if you want, you can use these check boxes for if you if you have implemented the design rule, you can check this. Otherwise, leave it. So it is a kind of checklist. That's it. Okay. So what is the first signal group? The first signal is DQ, DM, and DQS. Okay. They are saying you have to implement the impedance profile for DQ, which is 50 ohm, DQS 100 ohm, and DM again the 50 ohm, right? We'll do that first. People who don't know which tool I'm using, it is Altium Designer 22.1, and if you wanted to get the free trial of that tool, I put link in the description. You have to just click there and register yourself. Within 24 hours, you'll get the license. PDN Analyzer tool is a separate license from Altium Designer. So for that, I have put a separate link. For purchasing PDN tool license, you have to click over that link. With that said, let's roll the intro. Okay, how to do it? I already told you, right? So go to the design, rules. What you have to do, you have to go to the width section and create new rule. Okay, you have to create a name here. Okay, so on width section, we're going to assign the impedance profile for single ended, right? What are the single ended available on these? One is DQ, another is DM, right? So this will be let's follow this thing, just kind of a standard, nothing else. So it is 50 ohm DDR underscore, right? DQ is what? Data underscore, let's say, what was the other signal? Other signal was control, right? Okay, other signal was DM, right? So again, if you remember, we have created a single rule from the, okay, I can show you later. So we have created a single net class which contains all the data pins, or you can say the DQ pins, and all the DM pins, right? So I'm just going to use that net class together. So it will be, okay, what are the other 50 ohm thing? Other 50 ohms was address, right? What are the other? We'll see from here. What are the other 50 ohm? Other 50 ohm were all the control signal and address, right? So control, right? Now here you have to assign the net classes. So for net classes, the first will be this address. Now I'm just going to create a custom query from that and use the OR operator as I told you on previous session, right? So we'll just copy this, paste. After address, we have data. Where it is? Here we go. Again, another OR. What will be the other one? Control, right? Which will be this one. Okay. So we have covered everything till here. Okay. Now we're going to assign the impedance profile, and this is our 50 ohm impedance for all the single-ended tracks we're going to use on LPDDR4, right? Now we're going to create for differential one, right? So for differential, what you have to do, you can see this one here. You have to add another rule. So that will be, because all the differential pairs are 100 ohm for LPDDR4, so this will be 100 ohm. What are these? One is clock, one is DQS. That's it, right? DQS and clock. So let's do that as well. So this will be for clock and DQS, right? So from here you can, like from the name itself, you'll understand, okay, these are the things. And here you have to select the differential pair class, and one is clock, right? Just create a custom query, just copy this, use OR operator, paste it, and this will be DQS, right? That's it. Apply. So these are, so till here we just implemented the first design rule, which is this one, right? Another design rule is what? It is related to clearance, right? So here they are saying you should know the width of the track, right? So again, how you can know the width of the track? Because width of the track you can already you'll understand only if you implemented the impedance profile, right? So we already implemented the impedance profile. You have to just apply it, okay, right? And you needed one width for 50 ohm and one is for differential pair, right? That's it. And you have to multiply it by 2 and 3, and you will get what should be the clearance constraint, right? So let's run this, because we did some changes on the design rule, and we'll see if there is some issue. Okay, it's a kind of heavy project, that's why it's taking time. Anyways, so just take any group, right? So here we have this 100 ohm and this single ended, right? We just route a single track from here. That's it, right? And you can see the width of this track is, you can just note down this one, right? Somewhere. Okay, it is 0.119. I already noted down, so don't worry. Similarly for differential, what you have to do, you have to just draw a stub. Okay, hold on. There is some issue. Okay, let me check. Okay, the issue is we didn't click on this one. Okay, now it will be fine. Okay, so I know that there is not any problem. So now you can note down this value as well, which is 0.086, right? So whatever the rule we will create with respect to these two width, it will be like 2 times or 3 times. We'll see that. Okay, now just you have to remove these two, whatever you have created. Save the project. All right. So we're going to create the design rule for clearance. Go to the design rules. Okay, so this is the clearance thing. We'll create another rule. Okay, so what should be the name of this one? Okay, this is for all the byte group, right? So what it is saying, you have to read this thing. So it is saying DQ routing trace width and spacing within the same byte group. So they are talking about within the same byte group, right? After that, they are talking about from different byte groups, from other signals, all the. So how we're going to implement these 3 design rules together? Okay, let's see. So what you have to do, firstly, this is for, this design rule is for, let me say, okay, so this is for byte group. So DDR underscore, or you can say data byte, okay, data byte group. All right. Now what you have to select here, you have to select a net class. Okay, what are those net classes? Anybody wants to tell me that? One will be this one, then we'll create it to custom query, then we'll use OR, just copy it, right? Because all these 3 signals will be covered on this data group 1, all 3 types of signal, right? What was those? One is the differential DQS signal, one is the single-ended data mask, another is single-ended all the data bits, right? Just copy it, paste, and this will be group 2. Another paste, this will be group 3, another will be group 4. All right, now remove it. Okay, here you have to implement that. So they are saying it should be minimum 2 times of the width, right? We're going to follow that because that is enough. It's like 10 mil of clearance between the tracks, right? So if you'll calculate that, what was the width? Anybody remember that? Right? It was 0.11 something, right? so 0.119 or something like that. If we multiply it by 2, it is 0.238 mm, right? We're going to apply it, 0.238 mm. Okay, there will be some exception that we will discuss later. Okay, so there will be some exception on these two that we will add later. For now, this is our design rule, and it will just create the same thing that we want, right? If that will create the because we are using OR operator, right? So that means there will be like clearance between within the byte group and other signal as well, right? We will verify that during the layout. Okay, this is one thing. Apart from that, we're going to implement another design rule that is for clock. Okay, so as you can see from here as well, so till now we have implemented design rule for this one. Another is clock, right? So for clock, it is saying it should be 3 times within the with other signals, right? So in other signal, they are also talking about the other clock pairs as well, because we are using 2 clock pairs for each DDR controller, right? If you remember that from the schematic, so we have to implement that as well. So clearance new rule, and that will be for DDR underscore clock. That will be net class, right? If you remember that. And okay, here we go. So on this one, you will not getting, if you remember from the schematic, we just assigned differential pair net classes on the clock. You're getting it? We didn't assign any net class there, right? So one way is either you can go back and assign the net class, or you can just select the nets of the clock, right? So what are those? One is this one, right? And you can just convert that to custom query and use the OR operator, right? Just double click on this, so it will be like selected, Control C, Control V, and this will be the positive part of the clock one, right? And again, it is kind of, it will suggest you, right? If you kind of creating the change. Another clock is for DDR0, another clock is underscore clock underscore CLK P, right? It is here. You can see that, right? Similarly, you can copy this and you can paste it here, and that will be N, right? So till now, we just assigned we just created the custom query for all the DDR0 clock, right? Now we have to do that for DDR1, right? So what you can do, you just copy this or paste it, right? And just change that to DDR1, right? And this as well, right? So these are all the, we just selected all the nets of the clock, right? This is a kind of bigger way, but you can go back and create another net class, and later you can on that net class you can create this rule, right? Okay, we already know that for 100 ohm differential impedance, what will be the width of the track, right? So for this one, the width of the track was 0.08 something like that, right? So if you multiply it by 3, it will be 0.25. Hold on, yeah, 0.25 mm, right? And enter, right? So again, we're going to create some exception on this design rule, but yeah, for now it is fine. Okay, so this is one thing. We'll create another clearance rule, and that will be for command and address and for control signal. Okay, I'm just going to create for both of them together. Okay, so the name will be same, DDR underscore A underscore CTRL. Now what you have to do, we have net classes, right? So we'll just select address net class, create a custom query, use the OR operator, Control C, Control V, remove this, and another is CTRL, right? This one. Okay, and this is again 3 times of the width. Okay, so 3 times of the single ended width, right? In case of data byte group, it was the clearance rule was 2 times of the width, right? Here it is 3 times of the width. Okay, so we also known as these rules can be we can name that 3W 2W rules, right? So these are the same kind of rules that we implement. Okay, so these are as per the JDEC. Okay, so if you multiply it with again, so what was the clearance? It was 0.1, right? So it will be approx 0.3 mm. You're getting it? Okay, apply. Okay, so these are all the clearance rules that we have implemented just now. Okay, let's discuss other rules as well. Again, in case of Altium, you have option to create a rule for the length, the maximum length of the track. But the problem is, I mean, because this is too much length, right? It is 35 mm, right? In our case, our target is we have to implement our like all LPDDR4 connection within you can say 25 or within the 30 mm range. You're getting it? So there is no point to implement these rules, but if you want, you can go there and implement those. So you have to just go to the rail here and match length, and you can create new rule here, right? Now here you will get the same option. You have to select the net class, and here you have to enter the length unit, like what will be the maximum length here. Okay, this is for matched length. Hold on. Okay, this is for length, sorry. You have to create new rule here. So for now, I'm just going to remove it. There is no required this one. Okay, this is for length matching. Okay, let's discuss that later. For length, you can see here you can enter the maximum length, and here you can assign the net class. So that means for this particular net class, all the length of the track should be within this one, right? There's no point of using that because we know that we're going to implement that within very far range of under this particular maximum length. Okay, so you can remove it from here as well. Okay, so here you can implement that rule. For match length, I will tell you that rule on the next session. Okay, so you can implement that if you want. Okay, here we are getting few errors. Now I'm just going to tell you one thing. So you have to take one decision out of these two, and what are these? Let me show you from this diagram. Okay, just imagine two situations. Okay, first situation is let's suppose this is our SOC. Okay, here we have these pads. All right, this is the differential pair. Okay, here also we have pads. Okay, now we have to find out this differential pair. Okay, what are the two options we have? We can't, I mean one is we can place one via here, one via somewhere here and find out that. Okay, but let's suppose I have to route that outside, because it is again kind of creating clearance constraint between these two pads. Okay, so one is because these are differential tracks. So what are the property of the differential track? It should follow the correct, hold on. Okay, it should follow the characteristic impedance, right? And that means the width of the track. If that width of the track will vary, the impedance of the track will change. You're getting it? The impedance will be like wrong. Okay, and because of that impedance discontinuity, we use that term impedance discontinuity here. Because of that impedance discontinuity, there will be a lot of SI problem, right? So I'm talking about we are following the clearance here. Whatever the clearance rule we have defined, we are following the exact clearance. Okay, we just kind of rigid with the clearance. It is okay if we can vary the width. Okay, so there's one way. Let's make it more thinner, right? Just route it from here, right? And then here at the outside, when it is like outside of the chip, we can again make them thicker. You're getting my point, right? So from here we are following the impedances, and here we have like like here we have thick connections, here we have thin connection on this end. So there will be like 2 or 3 impedance discontinuities on this small cross section. What is another option? Another option is, let's suppose I can draw that bigger. Okay. Another option is, let's reduce the clearance. Let's reduce the clearance. Then we can route the exact width of the track which is following the impedance profile. So here impedance of the track is fine. Now when we reduce the track, what is the thing? Like how coupling, or you can say interference or crosstalk works? Anybody wants to answer that? Okay, so it is electromagnetic coupling, right? Whenever 2 tracks are running parallel, I already told you, it has the capacitive coupling and mutual inductance, right? Because we have inductance running here. And because of these two, a small amount of current will induce on another track, or you can say the silent one, right? If this track is functional, or there is a signal, high frequency signal is running on this one, so we needed this kind of coupling. Only then there will be like a small amount of current induced, right? But here the thing is, our track is coupling with only this cross section. You're getting it? This is very small. So the coupling between the via, okay, so here I am just noting down those points. Via, another is pad and track. That coupling, or you can say the crosstalk or interference, will be very, very less because of the area of overlapping is very less. You're getting it? So this is common sense, and that's why instead of, because if we'll change the impedance profile, there will be like for sure problem, right? Because we are dealing with very high frequency track and we don't know which track will create issues, right? That's why like the modeling or simulation of high speed layout is very important. But yeah, out of these two options, as a like hardware designer, we know that okay, here we don't have that much coupling, so we have to choose this option. We have to reduce the clearance rather than reducing the width of the track. Okay, so these are the exceptions. Okay, so the same thing you are getting here. Okay, so these are the errors we are getting because we didn't implemented the exception. Okay, and the exception is the clearance between via and the pad, sorry, clearance between via and the track and pad and the track. That's it. So what we will do, we'll go back to design rule, and whatever the clearance we have defined, we'll just make few exceptions here for this one, 0.1 mm. Okay, how I know the 0.1 mm thing? Because these are the minimum size of vias that we can manufacture. You're getting it? So there can be, I'll show you that there is another small size of via that we're going to use for signals. But again, there will be like not much difference from the vias we are using for power supply. So from here I got to know, okay, 0.1 mm or you can say 6 mil around, right? This is the clearance that is enough for this one, and it is manufacturable. So yeah, this is not like just guess, right? This is properly analyzed exception we are putting here. You're getting it? Similarly, between the via and the track, via and the SMD pad, right? And via and the through-hole pad, right? We'll just do the same thing for clock case, SMD pad and the track. Okay, so you can see the unit is mm, so you don't need to write mm on each case. So let's do that quickly. You got my point, right? So we are not just randomly changing these things. Okay, and this will be again 0.1. And again via and via, but we know that we're not going to place multiple vias together. And differential, for differential we're going to follow this thing. Let me show you that as well. So when we'll route a differential track from here, right, one is here, one is here, right? So how to place a via on the differential track, right? It will be like this, right? And then another layer will be routed like this, right? This is the right way to place via. Okay, so Okay, so we made that change, apply. Okay, so let's execute all these DRC and let's see for violation. So this is the most difficult part in terms of design rule and layout, you can say. I mean, out of all, compared to all layout. Okay, so here we are getting this thing. Let's adjust that. So now it will be fine. Okay, let's see if we are getting error somewhere here as well, right? So again, you don't need to put like so many extra extra exceptions, because then there will be like no point to creating design rules, right? So just think about those points, just because you are getting errors and you have to remove it. Don't do that, don't think like that way. Okay, and you have to see, like, if you are doing that particular exception, what will be the issue because of that. Okay, so it is like small things. Anyways, now we can start the layout quickly.